Please put your hands together for Dr. Viviana Acquaviva.
All right, well, so nice to be here, guys. Thanks for the invitation. So I'm gonna switch gears a little bit, and I'm really excited about being in this crowd that is obviously so passionate about astronomy. So as Dan mentioned, I'm part of the City University of New York. I'm on the faculty floor. I also put my email address here, so if later on, either you have questions that come up with, or you just want to get in touch for any reasons, clearly you are welcome to. So, well, this is a crowd of experts. However, I always like to start talking about what I still think after many years in this field to be like the most amazing fact ever, which is the fact that when you look at a star, and guess what this is?
The sun.
Yes! I know it's a much crappier picture than the one that but at least it was more active. And as you know, like light gets to us from the sun, and I'm sure that all of you know, at least the people in the first 3 rows, the distance from the sun, which is
93 million miles.
very good, or 150 million kilometers. Hey, this is science, we use the international system. And if we want to calculate how long light from the sun takes to come to us, what do we do? Take this distance and
Divided by the speed of light.
divide by the speed of light. Very good. Now we get something like about 8 minutes. Now we know we can keep playing this game and say that rather than looking at the sun, now we'll look at the nearby galaxies such as Andromeda. Photons from Andromeda come to us. Now what is the distance to Andromeda? Usually this is a more difficult question, but I have faith.
2.5 million light years.
2.5 million light years, and this is why we have this convenient unit of distance, so that the time that it takes for light from Andromeda to come to us is about 2.5 million years. So when we look at Andromeda, we are looking at a picture that is about 2.5 million years old, which may seem stale. On the other hand, on the time scale of galaxies, this is not much. But it really brings us to the point that I think makes astronomy really special with respect to all the other sciences, which is the fact that looking far away means that you're looking back in time. And I think that this makes up for the fact that you can't do astronomy in a lab, compared to many other sciences like physics, chemistry, biology. You can go in a lab, you can do experiment. You can't recreate almost any of the interesting situation in astronomy in your own lab. However, I feel like that in return, you get this unique ability of looking back into time, which is, if you think, to me, is still mind-blowing. So, how far have we looked back in time? So here what you see is a little chart that shows you time here along this line. So this is the present time, and this is going back in time. And so we have about 13.7. I guess from one of your next speakers is going to argue there's 13.67. 2 significant digits, 4 significant digits. Wow. So this is like the time elapsed from like the Big Bang to today. And this is sort of the situation before we were able to launch space telescopes. And so at that time, we're talking about the 90s, with ground-based observatories, we already knew about galaxies which are about, I shouldn't say 6 billion light years away, but they were seeing as they were 6 billion years ago. Now, the fact that I can't say that these two things are, like proportional to one another with just a factor of speed of light is the fact that the universe has also been expanding in between. But, you can still think about it as something like, several billion light years away. And then with the Hubble, which was launched in 1995, we've actually been able to look at galaxies that were now seen about 12 billion years ago. And so we're only talking about 1.5 billion years after the Big Bang. And then we didn't have another telescope in space. So what we did is realizing that another thing that you can do, if you can't have a bigger bucket to collect your photons, you can actually keep staring at the same spot in the sky over and over. And so we created this we called deep fields with the Hubble. So this is like a Hubble ultra deep field, and we continually imaging that same region with the Hubble until like dimmer and dimmer source started popping up. And the best that we have done so far, actually something that we weren't even anticipating to be able to do, is to see a galaxy that is now imaged only 200 million years after the Big Bang, or when the universe was only 5% of its current age. So I feel like this is, maybe it's also because I study galaxies in particular, and so the fact that you have this object that track the entire evolution of the universe is quite remarkable. However, I guess that the deal is, from there, we get a chance to observe the history of the universe and see how different objects have changed through time. So what I like to focus on is, okay, what have we learned so far? This whole looking at all these galaxies at different distances and observing them at different snapshots of time. What do we know? Well, the main things that we have learned is that the universe has been expanding, and in fact, we have sort of like promoted the evidence for this to a scientific theory that we call the Big Bang theory, that I'm sure you've heard about, not just a TV show, but the actual model of the universe, right? So what does it say? Well, the idea is that if you admit that the universe has been expanding, you can also rewind time, right? And so you get back to a point where you have the universe, which is now like very young and very hot, because all this energy that we have now spread out over a large volume was concentrated in something that was quite small. And if you wanted to measure, right, or to infer how fast the universe has been expanding, the thing that you will have to do is to understand which are the forces that come into play, which are the forces that regulate the expansion, and how they are in respect to one another. So here it is, there are like two of them. One is pushing outward and one is pushing inward. So which one would be the one that goes outward? What propels a universe to expand?
Dark energy.
Well, this is the beginning though. We are talking about primordial universe.
Nuclear
Radiation pressure.
Radiation pressure. So this is a pressure that we can think of as the initial momentum of the expansion. Right? It's not really a bang in the sense that there is no explosion, but there must be something, although we're really very far from knowing what that something is, that propels the initial expansion, right? You have like an initial momentum. And then you have another force that is trying to create this advocate, and is trying to prevent the expansion from proceeding, and what would that be?
Gravity.
Gravity, right? That's the easy one. And so the balance between these two components can tell us about the rate of expansion of the universe. Right, so, for example, if I ask you, okay, if I put more matter in the universe, with respect to, what is there today, what do you think will happen to the expansion? Would it proceed faster or would it proceed slower? Okay?
Slower because of the increased mass, which would cause gravity to be higher.
Right. With more matter, universe is more dense, gravity can take the upper hand. And in general, would you expect from these two that the expansion would be accelerating or slowing down? Slowing down, that's because you have an initial momentum, and then you have Newton's first law, which tells you, well, if there are no forces, things will either stay at rest or keep moving at a constant rate. However, here you have this only one force that we know of, which is gravity, that is trying to prevent the expansion, and so the only chance is slowing down. And so what astronomers sort of set out to do, and this was about 20 years ago by now, was to weigh the universe by measuring how the expansion was slowing down. They figured that it's because of dark matter, which it's all another talk, but you may have heard about it. It's very difficult to count the total mass in the universe by counting objects, because if you add together all the stars and all the galaxies, you get a number which is much smaller than what is really is there. So they thought, hey, you know what? All the mass produces gravity. And we know that gravity slows down the expansion. So let me measure how the expansion of the universe is slowing down, and this will tell me an unbiased balance of the total amount of matter in the universe, which seems like a great idea. So how can we do that? Well, they decided that the way to go was to measure the rate of the expansion, and so they thought, okay, let's measure the distances to different objects. So we now learn that galaxies exist at different times, so we are seeing them at different moments back in time. So they figure, let's go out and measure the distances to this object, and from there, we'll just have like a little graph that shows distances and how they vary with time, and this is, as we learned earlier, velocity. Now you see the first problem that you have. So if you go out with your telescope, look at a star, get out your little book, and you can note down the brightness of the star, which is all that you're able to measure, right? You look out either with your eyes or with a telescope. All that you can record at that time is how bright this object appears. So in some sort of, arbitrary universe, let's say that this object is bright 20. Now if you have another star, which is much smaller, so it's less luminous, but it's closer, and you look at it, as you know, you may find out that it has the same brightness. But it doesn't have the same brightness because it's the same. It just has the same brightness because, excuse me, even if it's closer, sorry, even if it's dimmer, it's closer. And you see how the game goes. I can have another star which is larger, that emits more photons. However, if it's farther away, I may look at my little notebook and still find that the brightness is the same. So the problem that I have is that stars, or really anything that I can think of as a tracker of distance, have different luminosity. And so if I measure how bright they appear, this is not enough to know how far away they are. I have these three variables, which are brightness, apparent brightness, we like to call it in astronomy, just to remind ourselves that it's not a physical property, it's just what it looks to us because we're looking at it from Earth, a very specific place. And then luminosity, and then distances. And so if I want to find distance, brightness alone is not enough. Now here's another question for you. If you had light bulbs instead of stars, would this work out? Could you trust that something that appears brighter also is physically brighter?
For the same wattage, yeah.
Right.
Wattage, yeah.
Right, if they have the same wattage, yes. Because at this point we have eliminated the difference in the intrinsic luminosity of the sources. And so if now I have like 360 watt light bulbs and I put them at different distances, I can trust that the brightness will be a good tracer of the distance, and I know how brightness varies with the inverse square of the distance. So the question for us is, are there things that are the equivalent of astronomical light bulbs? Are there things for which we know the wattage? Yeah?
C-field variables.
C-field variables, these are very good. We have something like that. The problem of C-field variables is that they are not, as objects, luminous enough that we can see them at cosmological distances. So we can see them in our own galaxies, we can see them in nearby galaxies, but if you're trying to evaluate the expansion of the universe, you need to be able to see farther, and so you need, as trackers, objects that are even brighter than that, where C-field variables usually have about 100 or so solar luminosities. So something like that, but more powerful.
Supernova.
Right, you need supernova. And of course, to figure out, the answer is yes, there is a specific type of supernovae called type 1a supernovae. And the supernova usually is explosions, and this is a simplification. Now we know several types of supernova. But the two main types come either from a massive star that gets to the end of its life and it explodes, not the case for us, or the ones that we're looking at here come from a white dwarf that explodes in a moment that we'll see more in a second. And the good things about supernovae that makes them superior, for example, the C-field variables, it was like a very valid suggestion, is the fact that for a period of time, or perhaps several weeks, this object can be as bright as an entire galaxy. They can get to a luminosity of 1 billion suns. And so these are things that even if they're very far, they're still going to be visible. And however, we know the stars are complicated objects, right? We've seen the stars have different luminosities. So why in the world should supernovae all have a similar luminosity? And the reason for that is that this particular type of supernova all comes from a similar life pattern, which is you have a star like the sun. Later on in its life, it expands to become a red giant, it sheds its outer layers, and it cools and contracts, and what's left of its core become a white dwarf. Now, if the white dwarf is in isolation, like our sun, for example, we know that there are no stars nearby, so unless something happens, our sun will sort of like, cool off and eventually become a black dwarf without a companion. However, if that star, the white dwarf, happens to be in a binary system, which means that there is another star orbiting nearby, and if the companion stars happens to be something like a giant, which is something with a large mass, but which is like fairly spread out so that its outer layers are not very gravitationally bound to that star, then the little white dwarf that is tiny but mighty, so it has very strong gravity, may start to slowly accrete material on its surface coming from the companion. Now, why is this relevant? Because a white dwarf is not just like a weird object with a gravity of 1,000,000 times the gravity of our own Earth, but it's also an object that is held together against the pressure of gravity, not by nuclear fusion like regular stars, but by something very weird that is called electron degeneracy pressure, which is a rule of quantum mechanics that tells that all particles need to have a seat. So like here, there's like almost all standing room. Now imagine that we say, okay, each electron needs to have a seat, which in terms of electrons means that each electron needs to have a definite set, a unique set of quantum numbers. And this just means that there is a limit to how tightly you can pack electrons in any type of matter. If you try to put more at a certain point, this would cause this matter to explode. And so for this type of stars, when the white dwarf gets to this limit called the Chandrasekhar limit, which is about 1.4 times the mass of the sun, the star has no other choice but to explode. Like the electron degeneracy pressure that has held the star against the crash of gravity suddenly is lifted off, and this causes something called a thermonuclear explosion. And the cool things about this process is that it happens all at the same threshold mass. And because of that, this type of supernovae tend to have very similar luminosities. So that's why they work out. So they have the two things that we want. They're very, very bright, so we can see them very far away, and they all come from a similar birth process, so that when they explode, they have similar luminosity. And so this is a little diagram that shows the light curve of several supernovae, like all plotted together, and this is days, so you can see that usually, once you get to the peak, you have about 2 or 3 weeks before it dwindles significantly. Now, this is something that usually astronomers don't want to show. It's not true that they're all the same, right? There is diversity also in this supernova. For example, if the initial stars have different composition, like some may have like a bit more metals, which are for us elements heavier than helium, some may not. So this is actually how the curves look like, if you were to put them in the plot without doing anything to the data. However, we call them standardizable candles, because we know that there is a relationship between the height of the peak and how wide the light curve is. So we can sort of like apply that correction and go from this plot to this plot, which is what makes these things work. So once we had this in place, we astronomers said, hey, we found this amazing thing. We have supernovae. We can see them really far away. Let's go and use them to measure their distances. And what they found was that all of them were dimmer than they expected. And in this case, because you can actually see this supernova also nearby, so you can read the wattage. You can say, hey, supernovae type 1a have a luminosity of, I don't know, whatever, 1 billion suns at the peak. And then, you see another one that is far away, if you have identified what kind of object it is, and you'll see that it looks dimmer than it should, then the only answer that you have for that is that it's farther away than you had previously thought. And this doesn't just happen for one, which could be a coincidence. This happened for all the supernovae that they had. And this was a big shock. And I feel like I always like to play a little bit of the sort of like reactions at the time, because something like that is something really that doesn't happen often. Like most of the time, I would say 99% of the time that in astronomy we set out to do an experiment. And we convince whatever, NASA, NSF, whoever is willing to give us money, to spend money into something. Usually it's because you already know 2/3 of the results, and you just need like the final push to get there. So getting a result that is utterly surprising and shocking, that you are sort of like afraid to tell your friends and colleagues about, is just not something that happens often. So let's see if we can, I want to play a little bit of an interview. The cool things also here, no, not this. Wait, oh my god. All right. I'd like to play a little bit of the interview to the two astronomers that were guiding two competing teams. So this was also the cool thing. It's like in normal cases, there will be like a group that has this result, and then it takes, nobody believes it, so it takes like 10 or 15 years before like other people try to replicate the result and cross-check and validate. However, here there were like two competing groups working at the same time. So it was really in their best interest to say, no, you're wrong, and this idea is crazy, and you got it wrong. But no, the fact that they both found this very surprising result actually caused the scientific community to accept it much more quickly than it would have otherwise. And so, these are like two of the three people who got the Nobel Prize in 2011 for this discovery, so only about 12 years after the papers were published.
Using the world's most powerful telescopes, two competing teams of astronomers spent nights scanning the skies for supernovae. Saul Perlmutter led a team of astronomers based in Berkeley, California. Brian Schmidt's team of researchers around the world included Adam Rees, who analyzed the data.
The whole project began about 20 years ago when we first set out to try to use supernovae to measure what we thought would be the slope of the expansion of the universe.
It was the prevailing wisdom that we would see the universe slowing down or decelerating in its expansion because the mass in the universe would act like a brake. Its gravity would retard the expansion. And so we thought the degree of that deceleration would essentially weigh the universe and tell us what its ultimate fate was.
There was a subtype of supernova that appeared to be very, very similar every time it exploded. If something is always the same every time, then it always reaches the same brightness. And that means that you can tell how far away it is by how faint it appears to you. And so if you find one, let's say, from 1 billion years ago, another one from 2 billion, another one from 3 billion years back in time, you can start looking to see how much has the universe stretched.
It was well known in the field at this point that there were two teams. One of the ways that it was apparent to us is we were using the same telescopes.
So you're passing each other, as you go back and forth, and now in relatively real time, you're hearing what's happening.
Sometimes we'd have the weather and they'd get weathered out. Sometimes they would be on the telescope and then turn it over to us when there were rain showers coming in.
There were times when people wouldn't give each other a hand, but it was still within this context of a fairly fiercely fought competition.
We had been collecting data at this point for about 3 years. So you take this massive amount of information and you try to reduce it either to one number or a yes or no question. And that's the fun and exciting part. Almost every day you succeed by having, in a way, less and less information. I wrote a computer program to tell me, so what is the mass of the universe that is causing that much deceleration, which I was assuming what was going on, and it reported that the universe had a negative mass. Now, the universe can't have a negative mass, but what that really meant is, hey, dummy, you should look at the data. It's not decelerating at all. It's actually the negative of deceleration. The negative of deceleration is actually acceleration.
Finally, by the time...
All right, and I also want to sort of like spend a moment commenting some of the reactions of famous astronomers at the time.
So you talked 1990,
in
something like
writing
that,
an article,
right?
that we are not very sure
98?
we are getting the right answer. How confident are we in this result? I find it very perplexing. You probably never will have another scientific result that is more exciting come your way in your lifetime. Start thinking of reasons that the distant Type 1a supernovae could be dimmer.
And this one also that I think is quite
A
interesting.
reasonable position for someone to take is that the observations are wrong. Andreas Albrecht, University of California at Davis. Its implications are so profound that they really need to assemble a more solid case. David Spergel, Princeton University. My own reaction is somewhere between amazement and horror. Amazement because I just did not expect this result, and horror in knowing that it will likely be disbelieved by a majority of astronomers who, like myself, are extremely skeptical of the unexpected. Brian Schmidt, team leader.
So
A reasonable position for someone to...
So, when we say team leaders, he was only like the leader of one of these two teams, and the third astronomer to get the Nobel Prize for this discovery. So, well, now it's almost 20 years later, and so we tend to trust this a little bit. And so, what is causing the acceleration is now the real question. And, when we didn't know why there seemed to be more gravity around than we thought, we said, okay, it must be dark matter. And so, sort of following a similar path, we said, something that we have no idea about, but actually has to account for 75% of the total energy of the universe is causing the acceleration. So let's call it dark energy. And this term really says nothing, right? You can see like it's a very nondescript term. It says that it's a form of energy, like all form of matter, all form of energy. So it just means that it participates to the expansion, and in this case to the accelerated expansion, and has the effect of stretching the space-time, which means that objects, rather than getting closer together, they will like get far away from one another at an accelerated rate. So, can I tell you something about what the dark energy is? I mean, I can perhaps share a couple of ideas. However, this is really in the realm of speculation. So, what I think is our best bet so far, something that was already predicted by Einstein, much before all of this happened, of course, but then he rejected it, calling it his best blunder, is something called a cosmological constant. This will be sort of like a uniform layer of energy that fills the space everywhere. And it's constant both in time and in location. So we can measure it here, we can measure it there, we can measure it in some other galaxy billions of years from now, and from here, and we'll find always the same value. However, I just want to mention two of the things that are very weird about the dark energy that I feel like sometimes they are not appreciated enough. The first thing is the following. Suppose that, you imagine the universe as a bucket, right? It's a bucket, this is actually a square bucket, but still a bucket. And you put some matter like these little particles in it. And then, with time, the universe expands. Right? So what happens to the level of matter? Does it go up or down? Down, right? If you have a bucket, you fill it with water, you stretch a bucket, level of water goes down. This seems to be pretty standard. However, if you do the same thing with dark energy, the universe expands, the level of dark energy stays the same. And that's why sometimes we think of it as a property of space-time, because it really doesn't seem to be something that fills the space, but really something that expands with the space. A bit like if we were to take this carpet and expand and it would have still the same color. So any property which is of the fabric itself will stay there, but if we talk about content, then this content should actually diminish in density. Not the case. The other thing is that, after all, this may not seem very surprising because we're used to forces that can be attractive or repulsive, right? So for example, if you think about the electromagnetic force, we know that unlike charges like one another, and like charges repel. So here what we are saying is we need something that makes objects not like each other and wants them to be spread more far apart. So what could that be in terms of the four fundamental forces that we know?
I mean, anti-gravity.
Right, something like anti-gravity. Right? Can we just, get this by having something that works like gravity, but with an opposite sign? And the answer is no, because unlike any well-behaved force, this dark energy, its strength and its amount does not depend on any property of the space-time. So, in gravity, we know that the driver of gravity is mass and distance. And so if you look at two masses, you need objects to have mass, and the strength of the force is directly proportional to the mass, inversely proportional to the square distance. The electromagnetic force works in the same way but with charge. However, there is no property of matter, of environment, anything really, that we can associate to dark energy to make it something that looks like anti-gravity. It does not depend on mass, it does not depend on distance, it's just constant everywhere for what we know. And so this is the other thing that is weird and makes it very unlike any of the forces that we know about already. So between then and now, have we learned something new? Yes. Well, first of all, we have better supernova data. So this is like the first set of data where these are just nearby supernovae that were used for calibration, right? In order to read the wattage, we have to look at ones that are nearby so we are not confused by the distance. So you have a set of calibrating supernovae that are close, and then these were the supernovae that were part of the original project, and like in going from here to here, you favor accelerating expansion versus like not accelerating. So you can sort of like, you need to analyze the data, it's difficult to read by eye, but you can see for yourself that it's not like that all the curves seem to be completely ruled out by the data that you have. So this is about 10 years later, so not even the most recent, but good enough to convince ourselves that now the data have shrunk, we have more data, we have smaller error bars, we can believe what is happening. And we've also learned that we have seen the epoch of the universe in which the transition from decelerated expansion to accelerated expansion happened, which is also a prediction of the cosmological constant scenario. So we've actually seen that 10 billion years ago, the expansion was not accelerating, which confirms that there is something new that has come up in the last half of the age of the universe, rather than something that was there from the beginning, so we got the whole scenario wrong. And now I guess one other thing that we could ask is, how else can we learn about the dark energy? Is there anything else, maybe besides the supernovae, that we can use? So to do that, I'll mention like a couple of things that I found particularly cool. One is something that you guys may know about already. So in the Big Bang model of the universe, one of the main things is like, okay, have a universe, rewind time, you end up with something that is small and very hot and very dense. So this primordial soup is an intrinsic prediction of the Big Bang theory. And so at that time, you have that, first you have like all the particles hanging out together and they form what we call like a tightly coupled plasma. And then at some point, the electrons, atoms can form, and photons, which are the yellow ones, are now free to travel and less likely to scatter off one of these particles, just because as the universe expands, there is more space available, so there are more trajectories that can be had. No, I don't think I want to update my computer now. Thank you, no. Thank you for the timely reminder.
I get that one on imaging. Drives me nuts, even when I don't even have it connected to the imaging.
That's why I never do anything with data, and all my stuff is like, okay, it can happen 15 years later. So here you have the yellow photons that are now traveling along. And these photons are something that we can find today. The only thing that happened to them is that they lost energy because as the universe expanded, they got colder. And so they are now observing much larger wavelength than when they were originally emitted. But we can predict exactly what that wavelength should be. And we found this in the form of the so-called cosmic microwave background radiation. Have you heard about that?
Oh, yeah.
All right, perfect. I figured so. So the cosmic background radiation is sort of like a very uniform radiation. In fact, it's the most perfect black body radiation that we've ever measured. And it fills space equally, however, not completely equally. What we think is that the photon baryon gas, which is like the tightly coupled plasma that we mentioned at that time, rather than being completely uniform, would have a so-called sound wave propagating through it. And the sound waves, are really like very similar to what we would imagine as ripples in the pond. So after that last scattering, after the photons basically can be set free from the plasma, what happens is that photons that happens to have a wavelength or like a separation that is exactly one harmonic integer of the size of the universal last scattering will actually propagate that perturbation in the uniform fluid. And so what you will see is that if you now look at the temperature of the photons over the sky, at some specific scales that reflect the size of the universe when that last scattering happened, you will find that there is a higher probability of finding like two either slightly colder or slightly hotter photons. And these differences in temperature are tiny. They're 1 part in about 100,000. However, we also have really good telescopes. And so after discovering the background radiation in 1965, what we saw for the first time in 1992 were actually these like very slight non-uniform patterns in what we call perturbation in the background radiation. And we had to observe it from space because, as you know, the atmosphere of the Earth is something that is really annoying when you have to do astronomy, which is why it took us some time. And so the first instrument that saw the pattern of the CMB anisotropies is COBE, the Cosmic Background Explorer. It was launched in 1989, and it was like an Earth-orbiting satellite that you can see there. And its resolution wasn't, it was great for the time. It was about 7 degrees. And so this is the map of the sky that you get from COBE. And, the galaxy, our galaxy will be here, so it's been removed. And you can see that there's definitely like a cold, hot pattern. After COBE, 1992, the next one was the so-called W map. And during this time, it was launched in 2003. During this time, we had gotten smarter. We had realized that it's much better for a telescope to to be actually farther away in one of the so-called Lagrangian points, which are like points of equilibrium between the Earth and the Sun. And so this one actually went to live at L2, which is 1.5 million kilometers away from Earth. And this was an incredibly successful mission. And this is the pattern of the anisotropy that we could see from Dablima. And for your viewing pleasure, I have a little animation that shows the improvement that you had from Kobe all the way to Dablima. So you can see all of these structures appearing, and astronomers used to talk about the findings like SH in this spot. They were supposed to be the initial Stephen Hawking, but we don't believe in that. But it's been like sort of the ongoing joke in the community for many years. And then the next one was the so-called Planck satellite, which was a factor of 3 better in resolution. And this is like the state of the art so far. It operated from 2009 to 2013. And again, I couldn't find something that did the animation, but I found this one. And so this is Dablima, and this is Planck. And so this is the best that we do today. And this is for us, in this sense, I want to stop it because I think it tends to give headache after a while. So the cosmic microwave background is a radiation that was emitted long ago. However, it's still sensitive to dark energy because what we are seeing is a special preferred scale in the sky, which is the size of the universe at last scattering. So this happened a long time ago, so this size is not sensitive to dark energy. However, what is sensitive to it is the distance between now and then, which gives us the angular size at which we actually see this pattern. In a universe with no dark energy, distances are shorter, and so this corresponds to a larger angular size on the sky. In a universe with more dark energy, distances are longer, and so we see the same physical size under a much smaller angle. And this is something that we've been able to do for a while. One other thing that we've only been able to do for about 10 years is to actually go and look at this special scale that is imprinted once and forever in the photons, also in other constituents of matter, in particular baryons. So remember that we had this tightly coupled plasma. The first thing that we saw were the photons. Some of the photons are a little bit colder, some of the photons are a little bit hot. However, this memory of a slight overdensity or underdensity was also kept by the baryons. And the baryons are just like the things that make up like the atoms and the stars and the galaxies and us. And so we realized that if I actually look at a map of all the galaxies that we've imaged, this is a map from SDSS, so it's like perhaps 10 years old. But if I look at all the location of galaxies in the sky, I take a ruler, I point my rulers on one galaxy, and I just make my ruler exactly as long as the size of the universal recombination. And I turn it around. Well, what I found is that it's more likely that I will find another galaxy exactly at that separation rather than at a random distance. The reason for that is that the baryons are also conserving the memory of that overdensities, and so these distances define a correlation that can be now seen in the location of galaxies all over the sky. So it's not just the photons, it's also the matters that 13.7 billion years later, because the last scattering only happens after 400,000 years from the Big Bang, still conserve the memory of that. And now this is amazing because we only have one cosmic microwave background, but we can look at galaxies at many different snapshots and many different distances, and this means many different instants in time. And so
there's many different ripples in effect.
Because there's
many different ripples.
Because that ripples can be seen, like basically you can imagine like find all the galaxies that have, that are still like 5 billion years ago. The ripples will be there at a different angular scale because the distance between you and 5 billion years ago is different, but you will see. And then you can do the same thing at 8 billion years ago. And this scale will have changed because now you're seeing under a distance which is longer, but still you can identify what that is. So every snapshot gives you a chance of measuring this correlation. And by doing that, because you know the physical size and the angular size is what measure to find the distance to that point. And so this is how we study not just the dark energy, we are able to find out not just the dark energy exists, but how it's been behaving over cosmic time. So this was like the first detection of the so-called Baryon acoustic oscillations. This is what they're called in 2005. And this is a picture from 10 years later, these are like the first data, the same data that we just saw, and this is how much we have improved since then. So now, we have all this observation, not just supernova, we have cosmic microwave background, we have Baryon acoustic oscillation, we put it all together. What do we get? Is the cosmological constant still working? After all, it's predicted by general relativity. It's one number. So it's pretty tempting to say, if it works, why isn't this the end of the story? And actually, the answer is yes, it works. So what they're saying here is a different scenario where these are supernovae data. These are Baryon acoustic oscillation data. These are cosmic microwave background data. And usually, in order to test the theory, you want all of them to point to the same location in parameter space, or in other words, to agree with one another. So this is a scenario of non-cosmological constant. This is another type of non-cosmological constant. This is the only one with cosmological constant. And this is the only one for which all the data are able to converge to one point. So yeah, it actually works quite well. So if you ask me, why don't you tell us that the dark energy is a cosmological constant? Well, I'll tell you, I feel like this is even more controversial than the other stuff. However, you would agree with me that Occam's razor is what really should guide us in science, because it's hard to tell that we have known the truth. The only claim that we can have is that we have found something that can explain everything that we observe. And maybe like future data will keep agreeing with that, and we won't revise our theory. Maybe we'll find new stuff, and then we'll revise our theories. However, I just think that simplicity is a great quality for a theory to have, right? This is, after all, the reason why we abandoned Ptolemy's model of the geocentric model, because he had like 81 epicycles by the end, in favor of Copernicus' model with the sun at the center, which could explain the same data, but in a much, much simpler manner. And so here, we want to abandon the idea of a cosmological constant, either if we found something that works much better, which we haven't, or we have a very good reason to suspect that that's wrong. And the reason that we have is something that we call fine-tuning problem, which is the fact that if you assume that the cosmological constant comes from general relativity, which was our theory of gravity, and you put together what we call a dimensional analysis, in other words, like you cook together the constant of gravity that you have to give you what is the expected energy scale of the theory, which is something that, say in electromagnetism works quite well. You do that, and you find that the expected value of the cosmological constant on dimensional analysis should be that big number there, which is about 120 order of magnitude larger than the measured value. And so for most theories, this is the most unsatisfactory aspects. And it's really a matter of taste how much this bothers you, right? Many cases we say, okay, and so you may have heard, for example, of the theory of the multiverse. And this is a theory in which we only live in one possible universe of many, many possible universes. And so in these cases, we just say, hey, we just happen to live in that universe where the cosmological constant has this value, but there are many more. So we don't have to explain why this one is so unlikely, because it's not the only one realization. So I feel like, the reaction to this fact is, really is a matter of personal taste. However, it's something that really sort of leaves a bittersweet taste when you try to say, okay, this is the final answer. And another thing that tends to bother people is something called the coincidence problem, which is if you put the three main sources of energy, which are matter, radiation, and cosmological constant, and you see during the evolution of the universe, which is on this axis, how they've been with respect to one another, and you consider this is a logarithmic scale, you see that at almost all times, you see like the other one decreased because, like matter, expands and so it goes down. Photon density, it also decreases just like matter. On top of that, they stretch and so they lose energy, so it decreases even faster. And then you have the cosmological constant that is like there, all constant, like lurking in the background, just waiting for the other ones to get low. So this is what finally happens. But you see that we live at the era indicated by this dashed line. And this is like a very, very uncommon circumstance instance in which the value of matter and cosmological constant are actually in a ratio that is not a huge number. In other words, there is not one source of energy that is exclusively dominating, while this happens for most of the time. And so some people feel like this is also a problem of the theory, that there should be a physical reason why now matter and dark energy are, you know, in a ratio of 1 to 3, as opposed to 1 to 100 or 1 to 100,000, like it happens for most of the evolution of the universe. Now, I know that you guys have time constraints, so I'm just going to skip this couple of things a little bit, which talk about what other thing could it be if it's not the cosmological constant. And you know, we can talk about it in like Q&A, if you like. I have nothing to do other than getting back on the train. And so let me just say, okay, what's the next step? Now that we know a little bit about, we know the cosmological constant can explain all the data that we have. We know that the expansion started decelerating and then accelerating. That this is, you know, I think what we should keep in mind is that we have so far only explored this part of the evolution of the universe. So I'm looking at, say, the last 6-7 billion years in terms of like measurements of distance through these methods. And so we have another long way to go. So one survey that, you know, I also happen to be a part of, but I'm really excited about is, and it's just started, it's called HEPTEX, the Hobby Everly Telescope Dark Energy Experiment. And so the idea is to map the distribution of 1 million galaxies at a median look-back time of about 10 billion years ago. So what we expect is that there is no dark energy there. However, you know, we found like big surprises once already, and so if we had to find that, you know, the expansion of the universe proceeding also during those times in a way that is unexpected, then perhaps this will give us at least some hints of, you know, what's going wrong and, you know, what kind of explanation we should be looking for. And, you know, I guess this is as good as they go in terms of possible explanation. It's possible that we are just like looking at the big elephant in the room from like different ways, different experiments, different aspects, different epochs, and we just have not been able to put the whole picture together. So it's a summary. Expansion of the universe is accelerating, very mysterious. The reason for that could that either the dark energy filled space or something that I didn't really have time to touch upon, but another, you know, all of our results were derived assuming that general relativity is correct. If that is not the case, that opens another avenue of investigation. So we have no clue about what dark energy is. We like a cosmological constant, but we can't explain why it's so small. On the other hand, none of the alternative theories of gravity that we could have worked, so we have work to do. And finally, to apologize for the lack of pretty picture, I thought I would put the fly-through of the galaxies in the Hubble Ultra Deep Field, and I think that this is a really amazing thing that, you know, we can have here. Is done by taking the galaxies in the Hubble Ultra Deep Field picture, associating a distance to all the objects for which a distance is known, and then they use this to simulate how it would be to fly through the galaxies. And so you can see how the density increases. And, you know, it looks like a simulation, but actually this is the real picture. So these are like the real galaxies put at the distances that we believe are correct. So, yeah, I know. Yeah. I figured that you would appreciate the how it goes. And now you can see.
Are we getting that next one, Shannon?
I think it's about 1 minute, so I think it's about 1 billion light years every 5 seconds.
Wow.
Right.
Wow.
And you can see how, you know, even like the little one now, we try to put the information that we have, but they also, you know, they change.
Is this a public video or no?
Yeah.
Can we get a copy of that?
Yeah, I mean,
I
can give
posted
it
this
probably.
before a few times on Twitter and Facebook. So
Right, yeah. I mean,
it's been out for a couple of years.
Yeah, it's on the Hubble website. Yeah.
It's on the Hubble website?
Yeah. All right.
When was the acceleration, when did it begin? When you said that there's a point in time where the acceleration of the expansion started.
I think that the equivalence between dark matter and dark energy, which, you know, marked sort of like the transition, is a ratio of 0.47, which corresponds to an epoch of 6 billion years ago.
So before the 6 billion, it was decelerating and then slowly going back up the curve.
Yes.
So, the deceleration started at the Big Bang.
Yeah, so well, I mean, we haven't probed to the Big Bang,
Right.
So I think,
But,
you know,
but
in this
presumably it started immediately decelerating because there was a lot of matter.
this is what we expect. You know, what I'm saying is like, you know, what now the scenario looks compatible with having, you know, the expected part where, you know, there is matter slowing down the expansion and dark energy is completely negligible at the end, like at the very beginning, because the universe is dominated first by radiation and then by matter. And so during this time it's decelerating. At the epoch where the dark energy starts becoming important as a source of, you know, as a contribution to the total energy budget, now, you know, because it's pushing the other way, then deceleration sort of slows, and then there is the inversion. But we haven't really probed this deceleration or the rate of it in the first, say, 5 billion years.
We haven't.
We haven't. So the data that we have are compatible with that. Like, you know, where, for example, I mean, well, the cosmic microwave background is a very early thing, but, you know, it's exactly where we expect it to be, you know, like the cross sections of, you know, electrons, photons, and protons are exactly where we expect it to be without anything else tampering. So. But we haven't probed it.
So, but this is all observation of what happened, right? You're really tracking down, there was first the acceleration, then acceleration. Then when will we know why it happened?
Science
Look
doesn't
at me.
answer why.
This is, yeah, I feel like the why. I mean, I guess, you know, we could give you a why. I mean, we know why the deceleration happened, right? Because there is this amount of matter and because of gravity. I think it's possible that we'll get to, you know, a similar explanation as opposed, you know, like maybe in 20 years we'll know about like a fifth force, so we have a grand unified theory that also has this dark energy. We'll find, I mean, the cosmological constant is predicted by GR, maybe we'll just have a good reason why it has this tiny value. You know, why? I feel like it's another. Yeah.
I was thinking about it. Do you ever hear about this idea, anthropic cosmology?
Anthropic principle.
Yeah, anthropic principle.
Yeah.
If you could talk about that, because I thought it was kind of fascinating with the coincidence paradox.
Exactly.
Right?
I think the anthropic principle is in general the idea that if, you know, we think that, so, you know, I guess we shouldn't be worried about something unlikely to happen. For example, the values of constants of nature, assuming like a value rather than another one, because of those constants has this value, we can actually be here. Like, you know, life was being able to arise on Earth, and, you know, we've been able to become a civilized, like an intelligent and advanced civilization, and so on. And so, in some sense, the fact that we are here is the reason for that, as opposed to the other way around. You know, like it could have, you know, constants of nature could have taken like 1 million of other values, but, you know, with the, I don't know, an electron charge which is slightly higher, you can have stable states of matters and so on. And so the idea of the anthropic principle is the fact that we are here is the reason why we can observe it. If those values weren't there, we wouldn't here to observe them, so why worry? It doesn't mean that they are unlikely. It's just, and I mean, I don't have a clear answer to that, although I do understand that it may seem unsatisfactory if you think that we live in a realization of the universe that seems to be extremely unlikely. And so I do think that a theory like the multiverse does alleviate this problem in saying we are one of very many. And so now we are the ones living in this one, which is fine, but there are many others which we're just simply not observing, in which, you know, other realizations are. But, you know, we still have only one universe. So cosmic variance, which is the inability, you know, the fact that you always have large error bars when you have small numbers, always catches up with us.
Yeah, your last image there showed things moving forward, expanding. How far back can you extrapolate in the periods where you haven't really observed? You know, how far have you gone, you know, basically run the picture backwards based on what we have now, and really going to close to the point of formation or
You can go
Big
right to the
Bang.
singularity, can't you?
We can't, we can't go past the cosmic background radiation because the universe before then is optically thick, which means that photons were just scattered, so they don't provide a window. So this is like the oldest radiation that we can see. Now the problem that we have is that there is an era, which is like say the first billion years or so, which is called the Dark Ages. The reason for which means that in a bottom-top scenario, in which first you form the small things and then you form the big things. You just don't have things to see, right? You have this bunch of atoms, and then they have to make stars, and then they make clusters, and they have to make galaxies. And you need something that is like bright enough to be able to be seen at these distances. So you also have this epoch in which galaxies have not been formed yet. And about this you can't see much, right? If you don't have sources.
And then one other comment is, at the Big Bang, there had to be some sort of acceleration for things to appear. I mean, there was deceleration, I know, in the earlier periods, but there was some
There was acceleration, is something
accelerating
that we call
factor.
inflation right after the Big Bang. So we think also that there was another phase of accelerated expansion of the universe, in which the universe actually, went up many, many times in size, that we call inflection, the first fraction of the second. The problem with extrapolating all the way to the Big Bang is that we don't have a way to test if any of the laws of physics hold. And so, we have these things that we call the Planck energy, and we say above the Planck energy we have no clue. We think that, everything, quantum theory breaks down. So I feel like, there should be a singularity, something where everything collapses, but we're also forced to admit that just before that, we get to levels of densities and temperatures in which the validity of the laws of physics just breaks down.
I'm not sure I can answer this right, but with the expansion of sort of space-time,
Yeah.
is it expanding like by Planck lengths, or is it Planck length itself expanding?
Well, the Planck length is like something that is like infinitely small, right? So the Planck length governs the physics
But
of the
is
very
space
small.
itself expanding, or is there becoming more space?
Oh,
I guess
space itself is expanding. So there are two things. Like becoming more space depends on the geometrical model of the universe that you assume. And in this case, we think that the universe is flat and infinite. However, what expands every day is the size of the visible universe, which is just like, the amount of distance that any photons born at the Big Bang can have traveled by now. However, what we are saying is that now, if, again, this was like the universe, and you imagine that you have one of these linoleum floors with the squares, the squares itself will be stretching. And so, galaxies are doing nothing but, sit at the corner of one of those squares, which just find themselves farther away from one another just because they are there.
But the square that you're standing on stays the same, because all the other squares around you could expand.
But from any point of view, you would see the same thing, right? So if I have a square, if you're here and you look around, you see one length, one length. And
getting more Planck length, so we
Never seen that chalkboard used before.
Oh, really?
Nope.
Oh, right. If you're here at A and you measure the distance to A, B, C, and D.
Getting more Planck units, right? So it's expanding a Planck length at a time, because it can't be anything smaller.
I mean, the Planck length is sort of the resolution
Right, I
of the
don't
universe,
think.
which isn't changing.
I do not think about this as like a discretized universe, though. I don't feel like that this is like an indivisible, like a basic unit. But so I would say that there are more Planck lengths, not that the Planck length itself is expanding.
Right.
Because I would imagine that, astronomers at any time, if they were to measure the physics of the very small, like quantum physics, I believe they would find the same.
Well, I'm trying to figure out if like the field density is getting less or less dense, or if there's just becoming more
There's no more matter coming into the universe.
Yeah.
Okay.
So the amount of matter radiation is decreasing in density. The problem is the amount of dark energy is not decreasing. Right? The amount of dark energy that we measured, say, 1 billion years ago is less relevant just because there was more matter and more radiation density. So it counts less, but in terms of energy density of dark energy, that's completely constant. It's just its relevance that is changing through time, because the other ones are going